In this video, we're going to talk about the second derivative of a function. Okay, so the second derivative of a function is the derivative of its derivative. So for a function y equals f of x, we use y double prime or f double prime or d squared y dx squared or d squared f dx squared or d squared dx squared of f of x to represent the second derivative. So the second derivative of a function is simply the derivative of its derivative. Now the derivative of the function, as we learned last time, and I started using this terminology in the last video, the derivative of a function is often called just the first derivative. Okay, so for example, we want to find f double prime of x, the second derivative, where f of x equals x squared plus 1 squared. Now usually, and again I've said this many times in this class, I don't want you to simplify things, right? Simplifying gives us another opportunity to make mistakes, and so often it's easier or better not to simplify if you don't need to. When you're taking a second derivative, often you're going to want to simplify. So let's take the first derivative. So f prime of x equals, we've got a chain rule going on here, so 2x squared plus 1 to the power 1 times 2x. So I'm going to simplify this a little bit, equals, maybe we'll leave it as 4x times x squared plus 1. Alternatively, we can multiply it all the way through. It doesn't matter, but let's leave it like this. So we're going to take the derivative of this function, which is going to require the product rule. So f double prime of x, the second derivative, is the derivative of the first function, which is just 4 times the second, x squared plus 1, plus the first function, 4x, times the derivative of the second, which is, oops, I've already made a mistake, which is 2x. If I wanted to, I could multiply this all out. We've got a 4x squared plus 4 plus 8x squared equals 12x squared plus 4. And let's just look for a second here. If I multiplied this one out, we would have had 4x cubed plus 4x. The derivative of this function, the derivative of 4x cubed, is 12x squared. The derivative of 4x is 4. So either way, we got the right answer. So when we're taking a second derivative, all we're doing is taking the derivative and then taking its derivative. Okay, now some new terminology, concave up and concave down. This is not actually the terminology I learned when I was first learning calculus, and I'll mention why in just a minute. But a graph of a function is concave up, and I learned this as convex, if the derivative is increasing on an interval. Now, if the derivative is increasing on an interval, the function must look something like this. Now, it doesn't have to be all of this, it could just be part of it. But this is a function whose first derivative is increasing. So let's just think about it for a second. Let's think about it over here on the left, right? Over here on the left, if this is our function f of x, well, the first derivative is negative because the function is decreasing, but it's decreasing at a lesser and lesser rate, right? So the slope of that first derivative, the first derivative is actually increasing on this region. Over here, the first derivative is positive, but the slope is getting bigger and bigger and bigger, so the first derivative is increasing as well. Okay, so that's concave up or convex. If f prime of x, the derivative, is decreasing, then the graph is called concave down. When I learned this, it was just concave, and I could remember concave versus convex as concave looks like a cave. That was my one way to remember these things. Okay, so let's think about this. So f prime of x is decreasing. So right now, this is our function. The function is increasing, which means the f prime is positive, but it's increasing at a lesser rate, so f prime of x is decreasing. And again, here, f prime of x is negative, and it's getting more and more negative. So f prime of x is decreasing as well. So a function that looks like this is concave. a function that looks like this is convex, or concave up, concave down. Now, we've just talked about increasing and decreasing derivatives of a function. We can think about increasing and decreasing by taking the derivative. So let's rewrite this or rethink about this. So if the second derivative of a function is positive, then we say the function is concave up or convex. Same thing, just slightly different terminology, same thing we just said in the last slide. If the second derivative of a function is negative, then we say the function is concave down or concave. So same picture, slightly different words. So let's look at this function. Here's our function, f of x equals x squared plus 2x minus 2. This is just a parabola, so we know what this looks like, but let's work through it. So f prime of x is 2x plus 2, and the derivative of this, f double prime of x, is just 2. So this function is concave up, right? It must look something like this, and of course this is a parabola opening upwards, so it does look like this. F of x equals negative x squared plus 2x minus 2. Again, we can do the same thing. F prime of x equals negative 2x plus 2. F double prime of x, the second derivative, is negative 2. This function is concave down. Must look something like this. And of course, this is a parabola opening downwards, so it does look like this. So we can see, using this second derivative, whether a function is concave up or concave down. Now, an inflection point is a point where the function is continuous and concavity changes from up to down or down to up. Inflection points are where the second derivative is not defined or is 0. Okay, so local extrema. Now we go back to that first derivative test we did before. If f prime of c equals 0, it's a critical number, but it's defined as well. So f prime of c is 0, and f double prime of c exists, then if f double prime of c is less than 0, then f of c is a local max. And if f double prime of c is bigger than 0, then f of c is a local min. Okay, so this is a really nice test. One last piece, if f double prime equals c, f double prime of c equals 0, then it might or might not have a local extrema. Okay, so this is the same as the first derivative test, and it's pretty easy. So let's look at some pictures. F prime of c equals 0, and f double prime of c is less than 0. Well, that means if we draw our function, we've got a function that must look like this, right? F prime of c equals 0, so the slope of the function is 0 at c, and it's concave down. Concave down looks like this, must be a local max. So here's c, here's our function, f prime of c equals 0, so the function is horizontal. F double prime of c is bigger than 0, it's concave up. This must be a local min, and this must be a local max. I tend not to remember the exact wording of this test. What I tend to do is go, okay, let's take the derivative, let's find where the first derivative is 0, let's look at the second derivative. If it's positive, must look like this, oh yeah, local min. If it's negative, must look like this, oh yeah, local max. If f double prime of c equals 0, then we're just not sure, right? We don't know what happens, whether the function is concave down and stays concave down, whether the function is concave up and stays concave up, or you could be in a situation where the function is concave up and switches to concave down. And then you've got neither a local max nor a local min. Okay, so let's find some local extrema. So f of x, the way we do this is we find critical numbers where the first derivative is 0, and then we see what the sign is of the second derivative at those critical numbers. So f prime of x is equal to 2x plus 2. Critical number, set this to 0, equals 2x plus 2. x equals -1. So that's a critical number. We need to find the second derivative. Second derivative is just 2, which means the second derivative of -1 is 2. Okay, so at -1, the slope is 0. It's concave up, so it must look like this, which means it is a local max. So f of 2 is a local max. Next function, f prime of x equals -2x plus 2. We set it to 0 to find the critical numbers. So 0 equals -2x plus 2. X equals 1 is our critical number. We take the second derivative, which is -2, the derivative of the first derivative, and f double prime of 1 is equal to -2, which means it is concave down, looks like this, which means we must have a local min at f of 1. Oops, sorry, this shouldn't have been f of 2. This one up here should be f of -1. Okay. Okay, let's do a couple more. F of x equals x squared plus 3 times 9 minus x squared. Take the first derivative. F prime of x equals, we've got a product rule here. We could multiply this all out, but let's just take the product rule so that the derivative of the first function is 2x times 9 minus x squared plus the first function, x squared plus 3 times -2x. I could take the derivatives here. I've got a couple of product rules, so it would work, but I think I'll multiply it out. I think multiplying this out is going to make life easier. So this is 18x minus 2x cubed plus, minus 2x cubed minus 6x is equal to 12x minus 4x cubed. Okay, take the second derivative, just so we've got it. Second derivative is 12 minus 12x squared. Okay, so we've got the first derivative, the second derivative. Find critical numbers, set the first derivative to 0. So 0 equals 12x minus 4x squared. So 0 equals, factor out a 4x times 3 minus x. Wait a second, I think I made a mistake. That should be cubed. 12x minus 4x cubed. Factor out the 4x, we get 4x here. That gives us a 3 minus x squared. So critical numbers at x equals 0, x equals plus or minus the square root of 3. Okay, second derivative. When x equals 0, f double prime of 0 is 12, which means that for x equals 0, it's concave up, so f of 0 is a local min. All right, f double prime of the square root of 3 is, well, 12 times this, that's going to be negative, certainly less than 0, so f of square root of 3 is a local max, right? Because here, less than 0, less than 0 looks like this. And we put in negative square root of 3, again, that's going to be negative, so f double prime of negative square root of 3 is less than 0, so f of negative square root of 3 is a local max. Okay, so that's all we're doing. Step 1, calculate our derivatives. First derivative, second derivative. Step 2, set the first derivative to 0 or find where it doesn't exist, find the critical numbers. In this case, 0 plus square root of 3 minus square root of 3. Third step, plug those numbers into the second derivative. We don't actually need to know the values, we just need to know the sign. So first one, f double prime of 0 is 12, means the function opens upwards, it's a smile, which means we have a local min. F double prime of square root of 3 and negative square root of 3, both less than 0, meaning we have local max. All right, one more problem. F of x equals x squared minus 4, the quantity squared. Step 1, take the derivatives. F prime of x equals 2 x squared minus 4 times 2x. I'm going to multiply all this out, so we've got 4x times x squared minus 4, which is 4x cubed minus 16x. So there's my first derivative. Second derivative, derivative of this function, 12x squared minus 16. Find the critical numbers. Set the first derivative equal to 0. 0 equals 4x cubed minus 16x. Factor out of 4x, 0 equals 4x times x squared minus 4. So x equals 0, x equals 2, x equals negative 2. Gives rise to 0. Okay, those are all my critical numbers. Calculate the second derivative, or at least the sign of the second derivative. F double prime of 0 is negative 16. Concave down means that f of 0 is a local max. F double prime of 2 is positive. 12 times 4 is bigger than 16, so that's bigger than 0. Concave up. F of 2 is a local min. And f double prime of negative 2, again, same thing, bigger than 0, concave up. F of negative 2 is a local min. So that's our process. Take the first derivative, take the second derivative. Often, it's nice to simplify the first derivative before taking the second derivative. Once you've done that, find the critical numbers. Set the first derivative to 0. Once you've found the critical numbers, plug them into the second derivative. You don't need to calculate the answers, you just need to find the sign. If the sign's negative, draw a little concave down frown. You see immediately it's a local max. If the second derivative is positive, draw a little concave up smile. You see immediately it's a local min. And that's our process for finding local extrema.